In this video, we demonstrate our project where we enhance the data reliability for time-sensitive traffic. This is how our overall setup looks like. We will be explaining it in greater detail now. We have the patient data acquisition module where we have a Raspberry Pi that connects over I2C bus to different sensors. The first sensor is an SpO2 sensor, the second sensor is an ECG sensor, and the third sensor is an IR temperature sensor. These sensors generate data which is sent over UART to the PC, and the PC runs a Python application. The Python application gets the patient data coming over UART and uses Socket API to generate UDP packets. These UDP packets are sent over to the SmartNIC using virtual interface. The SmartNIC on PC1 then duplicates these packets and sends them over its two physical ports. These two physical Ethernet links connect to two different Raspberry Pis. These Raspberry Pis are named FRER2 and FRER1. They can be thought of as different cellular devices which connect to their respective SSIDs, which are handled by the two routers named FRER2 and FRER1. These can be thought of as different mobile base stations. These routers then send out these packets from their WAN side into an Ethernet switch. This Ethernet switch is responsible for aggregating these packets and sending it over to the third link. This can be thought of as the back-end network. The third link then goes to the physical port of the second SmartNIC. This second SmartNIC is responsible for the deduplication of packets at line rate. Only the original packets is sent over to the virtual interface, which goes to the end application. The benefit of using this scheme is that both the sender and receiver side application are agnostic to the duplication and deduplication happening in the network. During the demo, you can see the sender and receiver screens. This is the transmitter side, and this is the receiver side screen. We have introduced 30% packet loss in the networks. The details will be shown later. Now, if we remove one of the Raspberry Pi from the network, we essentially have only one Raspberry Pi link offering 30% packet loss. You can think of this as a single operator being active, and that offers a quality of service where 30% packets are being lost in transmission. In this demo, you can get an idea about the quality of service we get in our application when we have 30% packet loss. So as you can see, in the end application, the live graph is being plotted, and that is experiencing discontinuities because of the packet losses. Now, if we reconnect the second Raspberry Pi into the network, we essentially have two redundant links. You can think of this as two different mobile networks sending over the data to their base stations, which are then finally aggregated and sent over to the hospital side. And we are doing a deduplication to receive only the original packets. Now it is clearly visible that the end application is continuously receiving the packets, and the quality of service has significantly improved. While keeping the packet loss per link at 30% as in the previous demonstration, in this demonstration, we'll be doing a quantitative analysis of the packets. For doing so, we have labeled the packets with the number from 0 to 9999, and we are counting the number of packets that are correctly received, the packets that are received along with duplicates, and the packets that are lost in transmission. You can have a look at the transmitter screen shown here and the receiver screen to your right. The packets are now in transit. Let us wait for the process to complete so that we can analyze the results. We have completed the transmission of 10,000 packets. Now let's proceed for the analysis. The packet count at the receiver is 9119 packets. We have to do a further analysis on this to find out if any duplicates were also passed through. So now we'll run a script that analyzes the received packets tag and gives us the complete statistics. So we have received a total of 9119 original packets, 881 packets were lost and 0 duplicates passed through. That gives us 8.81% packet loss. Let's look at the packet count per link. We have configured 2 registers on the receiver SmartNIC to keep a count of the packets received per link. And as expected, we see a 30% loss of packets on each of the links. Coming to the implementation details of packet loss, first we connect to one of the networks. Then we do a SSH login into the Raspberry Pi on that network. After doing that, we run a NetEM tool on the Raspberry Pi to do a 30% packet loss on the wireless link. Similarly, we connect to the other network and run the same tool on the other Raspberry Pi. The implemented network topology is shown here in greater detail.